Okay, good afternoon. My name is Dan Arellano. I'm an Associate Director of Maintenance at Stanford University's Energy Operations Department. And I'm going to tell you a little bit about how we implemented, I got to read this because it's a mouthful, how we implemented an element of predictive asset maintenance monitoring within the Internet of Things. Okay, got that out of the way. A little bit about me. A long time ago, I graduated from the United States Merchant Marine Academy in Kings Point, New York, with a Bachelor of Science in Marine Engineering. I spent the bulk of my career at Calpine Corporation. I was a general manager of several combined cycle power plants in the Bay Area. And I also managed the major maintenance of an aeroderivative fleet of gas turbines. I moved over to Stanford University around 2014, and what was happening over there was, they were in the process of what they call their SESI program, which was the Energy Systems Innovation Project. And what was happening is they had a combined cycle power plant running there that was going to be ending its life, and they were looking for a new solution of how they're going to address their energy needs. The plant provided chilled water, steam, and electricity to the campus and the hospitals. What SESI did was it came in and replaced it. The way it did it was it got all the electrical distribution through a high voltage, one single high voltage yard. And to get power production, Stanford actually went out and built a 67 megawatt solar generating station in the middle of the Central Valley. We also put in 22 miles of underground cooling and heating water to all the buildings, which replaced the steam. 150 buildings were converted from steam to hot water. And we built a small process steam plant because the hospital still needed steam for their operations, and also the central energy facility. And you can see what it utilizes is thermal storage. Those two great big tanks can hold chilled water, about 10 million gallons in chilled water and about 4 million gallons of hot water in the red tank. We also put in some heat recovery chillers. Those chillers actually are very efficient, and they can heat and chilled water in the same operation. And also at times when we can't always run those heaters because of storage requirements and loads, we have a conventional heating plant, which is just conventional chillers, cooling towers, and some hot water generators. Okay. And SESI had its benefits, of course. Reduced fossil fuel consumption dramatically, greenhouse gas emissions ridiculously reduced. Campus water use was dropped a lot because of the cooling towers. We no longer use them. We no longer spray the water into the air or put it down to drain. And basically 150,000 tons of CO2 not being consumed every year, or not being, let's say, emitted every year. Okay. SESI had a lot of good things. There was a lot of innovation, but what they didn't apply when they are constructing or making the facility was any type of, any type of predictive maintenance monitoring. They had great asset monitoring, system monitoring, process parameters, forecasting, plant operation, but there was nothing there for a maintenance guy to go in and say, hey, I want to look at my machines. I want to know how they're operating, or they're about to fail, or any kind of parameters. Everything was based on a control room. You get an alarm, some process alarm happens. You have techs walking around. They'll respond to the alarm, and if it's something that there's a problem with the machine, they'll fill out a work order. They'll call somebody to go down and look at it. It's very subjective. A lot of times it depends on who the operator is, whether he catches it and calls you, and it depends on who's the tech who's making the rounds. If he happens to walk by a pump when it's making a noise, or he notices a leak before it's too late, or becomes a bigger problem. So potential results were there's potential for missing something big. One of the wake-up calls I got there when we first were commissioning the plant, we were having some issues controlling temperatures, was our energy operations management got called to the laboratory of a Nobel laureate. The Nobel laureate patiently explained to us that he's mapping and imaging molecules and atoms, and the way he does it is just on this big table with a bunch of fixtures and all these different lasers. And he'll shoot the fixtures, these lasers, for about hours at a time, and all downloads in computer. Then he'll switch the lasers, and he'll shoot it again. And he says to do a single molecule takes like a month for him to like completely image it and get the data. So apparently, while he was in the middle of this experiment, there was a temperature spike in the cooling system. The table and fixtures, expanded a few degrees, a couple of angstroms. Totally wiped out his whole project. He had to start from scratch and do it again. So he wasn't happy, and he made it clear that, we had to improve. Okay, so again, more critical applications are the central and facility powers 200 buildings on campus, classrooms, research labs, dining facilities, offices, residences. We also supply a medical school and 2 hospitals. And again, another story. When this plant's designed, you don't want to build a complete heating and cooling plant for one day a year that you're going to be able to supply all the needs. So what you do is you build thermal storage, you use it effectively. But of course, if you're going to have like 100-degree weather for 15 days in a row, you're going to run out of chilling capacity eventually. And that's what happened last year. For a couple of hours, we just exhausted all our ability one day to make it. And they actually had to cancel all the operations in the ORs in one of the hospitals for a couple of hours. So there's a lot at stake. So what was our plan? What did we want for these machines that were not getting monitored? Of course, we wanted automated data. We wanted something where we didn't have to send a tech out to take readings or manually download information. We wanted to make it frequent and reliable. We wanted it simple. We didn't want to have to go reconfigure our entire control system so that certain machines can feed into it and we can pick up the parameters. No system integration if we could help it, no permits for wiring, and we wanted to make it IT friendly. We didn't want to install something and IT comes back and says, no, you can't do it, the Koreans are going to steal our research. So, and then also automated analytics. We wanted to be able, I didn't want to rely necessarily on in-house capabilities. I wanted to have it run through a program. It finds alerts. It sends the alerts out to the people who need to see them so they can take action. And also remote access and data alerts. I didn't want the guy in the control room sitting there and telling me when things are happening. I can get it. I can send emails to people. Hey, we got a high vibration alarm. You can look it on your cell phone. You can look it on your iPad. And you can look it on your computer. One button click takes you right to the app. You can see the piece of equipment and what the situation is. And it's out there. We found it. We found that there are wireless vibration sensors that can be employed. Easy cost, you just clamp the thing right on top of it. That there's a cloud infrastructure. I don't have to go and invest money in servers and patches and refresh. And if you guys have been dealing with servers, you know that it's just not a server. It's like a bunch of other time and money aspects to it that you have to maintain. And also, there's analytics software out there that you can take that data from that cloud, analyze it, and give you the results that you want. And here's what we did. Pretty simple. Put the wireless sensors on our machines. One thing we did have, since we do automated rounds, is we already did have a Wi-Fi system through all our machinery spaces. So it was an easy connection from taking those wireless sensors and putting it in through our Wi-Fi. The Wi-Fi takes it, sends it right to the cloud. I don't have to have a server. I don't have to worry about the data. The cloud, and then the app interfaces with the data in the cloud, analyzes data. I can configure it to when I want to get alerts, who I want the alert sent to, what levels. And it's also a good historian. When you have a problem, you find it, you write in what you found. So the next time you get an alert, you're like, oh yeah, that happened, here's what we did. Does it work? Well, it does work. One story I like to tell was 5 o'clock in the morning, everyone gets an email, the people on the distribution list saying we have a high vibration on a circulating pump. Fill out a work order, technician goes down, takes a look at it. He's like, Dan, I went up and down this pump. I can't find anything wrong with it. It's running, there's nothing mechanically wrong that I can see that, I can't even tell if it's vibrating. It's like, okay, great. So the next step is, all right, so I tell the controls engineer who can access the data historian of all the process, features and how the plant was running. He runs it through and he notices that, hey, apparently during that time we had the high vibration. The process controls decided to deadhead the distribution valve, so that pump is cavitating for 3 hours, right? If I didn't have that system in place, I was relying on somebody walking by and noticing it was making noise, or else I never would have found it. So a quick overview of what we did and other things that we caught. That was just isn't the only thing, we had a bunch of little things. In January, we deployed wireless devices on over 25 of our critical pumps. Those worked well. We liked the interface. We liked the data we're getting, so we expanded it to our cooling towers. Like I said, we caught that first defect in October, first big defect. There are other things. And then also in November, we noticed that we were getting a weird signature in one of our cooling tower gearboxes. We determined, after looking at it closer, that it was wearing out. There was a bad tooth or something inside of it that's wrong. Rather than having it failing in the middle of the summer when I was going to need it, I was able to say, great, made sure a spare was on site, and next month, as part of our regular PMs, we're changing that out. And then up another one, we got a shift in vibrations, gave us an alert, sent the tech down. He looks at it, and he says, hey, a coupling was about to fail. So he goes in, he changes it on our time when we wanted to. So it works. How does it work? Well, pretty simple. Unplanned downtime is decreased. Right? What may have taken hours or weeks to repair, depending if you have to mobilize and get parts, the days and weeks to repair, now can just take hours. You go in, you fix it before it becomes a big problem. O&M costs reduced. To have the same type of surveillance that we're getting now would require, sending guys out, taking readings, analyzing data, having servers. So it's actually less expensive to employ this technology the way it is than any other traditional means that I know of. And of course, repair costs reduced. You catch it when it's early, before you have a big failure, and overall reliability as a result is improved as well. Key lessons learned. Looking at this, first initially you're thinking like, oh, we got to interface all our machines to our control system, get into our data historian so we can crunch these numbers and find out what's going on and what's that going to take. And you soon to realize every machine's different, every machine's going to require a different interface. So you start looking for more simple, so you kind of gear back your expectations, you start looking for simpler solutions. So clearly there was a business case, we had to get it done. So we focused on, well, we can't get all that done. That's going to take $1 million in 3 years. Let's see what we can do. So we found this application. It's as simple as sticking a remote on top of a piece of equipment, configuring it, so it goes to your internet and into the application. Right now, if we wanted to put a new mode in, it's a matter of hours. Like you find a piece of equipment that's lying around that you want to monitor, take a mode off the shelf, you stick it up there, and you're getting instant data. And also involve IT early, especially at Stanford. They're very, very, we get attacked every day from somebody trying to get into our data. Involve them early, explain out what you're doing, because the more they know in advance, the less pushback you're going to get when you just tell them what you're going to do, because then they're going to tell you, no, you're not, because you're not going to have that done here. So get them involved early. So what else are we going to do with this stuff? There's other equipment we want to put some instrumentation on. The chillers and hot water heaters, they do have like internal HMI controls that do pick up vibrations, but we're finding it would probably be a lot easier just to install one of those and try to get them in through our control system. Explore other parametric monitoring solution. Right now we just have vibrations and temperatures, but what else? You can monitor like VFD parameters, you can stick things on steam traps to tell you if they're failing, and also electrical panels, you know, whether they're hot, they're vibrating, if they've got power surges, all types of different applications. And ultimately, right now we're working it through our EAM system, but can we, and there is a way to actually, rather than having to get an alert and issuing a work order, you can get an alert that will issue a work order automatically for you. We're not there yet. There's a lot of noise yet. We don't want like 50 million work orders coming out. That really just you need one. So we're working that system out too to incorporate it better into our workflow. And thanks.